In the vast expanse of our solar system, where the delicate balance of gravity and motion governs the dance of celestial bodies, two remarkable comets have captured the attention of astronomers and stargazers alike. One, a fragile visitor from the outer reaches of the cosmos, meets its demise in the blistering heat of the sun, while the other, a resilient traveler from beyond our stellar neighborhood, defies expectations and survives against all odds. These two comets, C2025 R2 SWAN and 3I Atlas, offer a compelling glimpse into the volatile and unpredictable nature of the solar system, a realm where survival is as much a product of fortune as it is of fundamental physics. At the heart of this cosmic drama lies a fascinating paradox. One comet, C2025 R2 SWAN, was discovered by amateur astronomers through the Solar and Heliospheric Observatory's SWAN camera. Its presence first noted in late March 2025, initially heralded as a potentially bright celestial spectacle. The comet was expected to reach a peak magnitude of around 5 by early May, making it visible to the naked eye under dark skies. However, as the days passed, its brightening stalled, and soon after, signs emerged that the comet was beginning to disintegrate. By mid-April, the nucleus had vanished, leaving behind a swirling cloud of dust and debris. This dramatic end serves as a stark reminder of the fragility of cometary bodies as they navigate the intense gravitational forces and searing temperatures near the sun. In sharp contrast, 3I Atlas, the third confirmed interstellar object to pass through our solar system, has carved a vastly different path. Discovered in July 2025 by the Asteroid Terrestrial Impact Last Alert System, ATLAS in Chile, this comet hailed from the depths of interstellar space, traveling at an extraordinary speed of 58 kilometers per second, far exceeding the velocities of the previous interstellar visitors, 1I Oumuamua and 2I Borisov. Unlike C2025 R2, 3I Atlas has proven to be remarkably resilient, maintaining its structural integrity despite the immense challenges posed by its close approach to the Sun. With a perihelion distance of 1.36 astronomical units AU between the orbits of Earth and Mars, the comet has endured the scorching environment and continues its journey toward the outer solar system. These two comets, though vastly different in their origins and fates, share a common thread. They both serve as testaments to the dynamic and often chaotic nature of the solar system. Their contrasting stories raise profound questions about the mechanisms that govern cometary behavior, the role of solar radiation and gravitational forces in shaping their destinies, and the broader implications of such events for our understanding of the cosmos. As we delve deeper into the science behind these celestial wanderers, we uncover a universe in constant flux, where survival is never guaranteed, and every encounter with the Sun is a high-stakes gamble. This is the story of C2025 R2 SWAN and 3I Atlas, a tale of destruction and endurance, of fleeting brilliance and enduring mystery. It is a narrative that invites us to explore the intricate workings of the solar system and the forces that shape the fates of the objects that traverse its vast expanse. In the following sections, we will examine the scientific principles that underpin these comets' journeys, the observational data that has revealed their secrets, and the broader implications of their existence. Through this exploration, we gain not only a deeper appreciation for the complexity of our cosmic neighborhood, but also a renewed sense of wonder at the ever-changing tapestry of the universe. To fully grasp the significance of C2025 R2 SWAN and 3I Atlas, it is essential to understand the fundamental processes that govern their behavior as they traverse the solar system. Both comets originate from vastly different regions of space, one from the distant reaches of our own solar system, the other from the interstellar void beyond, but they are united by the same cosmic forces that dictate their fates. At the core of their journeys lies a delicate balance between internal structural integrity and external environmental pressures, particularly the intense gravitational pull of the Sun and the radiative forces that act upon them. C2025 R2 SWAN was first detected in late March 2025 by amateur astronomers analyzing images captured by the Solar and Heliospheric Observatory's SOHO Solar Wind Anisotropies SWAN camera. Initially, the comet was expected to follow a trajectory that would bring it relatively close to the Sun, with a perihelion distance of approximately 0.5 astronomical units, AU roughly 75 million kilometers. At such proximity, the comet was anticipated to undergo significant heating, causing its volatile materials to sublimate and release gas and dust, creating the characteristic coma and tail that define cometary activity. However, unlike many comets that maintain stability despite these conditions, C2025R2 proved to be exceptionally fragile. By mid-April, observations revealed that the comet was no longer exhibiting the expected brightening pattern. Instead of intensifying as it approached the Sun, its luminosity remained stagnant, and by early May, the nucleus itself had vanished. The most plausible explanation for this sudden disintegration is the fragmentation of the comet's core due to thermal stress and tidal forces exerted by the Sun. As the comet neared perihelion, the intense solar radiation caused rapid sublimation of its icy components, leading to the buildup of internal pressure. If the structural cohesion of the nucleus was insufficient to withstand these stresses, it would have fractured, scattering its material into a diffuse cloud of dust and gas. This process is not uncommon among comets, particularly those with weakly consolidated nuclei. Many comets, especially those originating from the distant Oort cloud, are loosely held together by frozen volatiles. When exposed to the Sun's heat, these materials sublimate at an accelerated rate, leading to instability and, in some cases, complete disintegration. C2025R2 exemplifies this phenomenon, serving as a textbook example of how even seemingly robust comets can succumb to the harsh conditions of the inner solar system. The discovery of C2025R2 also highlights the importance of early detection in tracking cometary behavior. Had it not been for the vigilance of amateur astronomers monitoring the SWAN camera images, the comet might have gone unnoticed until it was too late. The initial observations placed the comet at a solar elongation of 28 degrees, meaning it was still relatively far from the Sun, but on a trajectory that would bring it dangerously close. As it approached perihelion, its visibility improved, allowing for more detailed observations. However, due to its proximity to the Sun, the comet remained challenging to track, particularly as it transitioned from the morning to the evening sky. Despite its eventual disintegration, C2025R2 provided valuable insights into the diversity of cometary structures and the factors that influence their survival. Its orbital characteristics suggest that it may have originated from the outer reaches of the solar system, possibly the scattered disk or the distant Oort cloud. With an estimated orbital period of thousands to tens of thousands of years, it is likely that C2025R2 had never before ventured into the inner solar system, making its journey a rare and transient event. The fact that it broke apart upon its first passage near the Sun underscores the vulnerability of such objects when subjected to extreme conditions for the first time. If C2025R2 represents the fragility of cometary bodies, 3I Atlas stands as a testament to resilience. Discovered in July 2025 by the asteroid terrestrial impact last alert system Atlas in Chile, 3I Atlas immediately stood out as a unique and extraordinary object. Unlike typical comets, which originate from the Kuiper belt or Oort cloud and are gravitationally bound to the Sun, 3I Atlas followed a hyperbolic trajectory, an indication that it was not native to our solar system but had instead originated from interstellar space. With a hyperbolic excess velocity of 58 kilometers per second, 3I Atlas is moving at a speed far exceeding the escape velocity of the Sun. This places it in the category of interstellar objects, of which only a handful have been observed to date. The most famous of these are 1I Oumuamua and 2I Borisov, but 3I Atlas is distinct in several ways. Most notably, its trajectory is extremely elongated, with an orbital eccentricity of 6.41, by far the highest recorded for an interstellar object. This means that 3I Atlas is not merely passing through the solar system. It is doing so at an angle that is almost perpendicular to the ecliptic plane, making it a rare and scientifically valuable object of study. One of the most intriguing aspects of 3I Atlas is its ability to maintain structural integrity Despite the extreme conditions it faces, unlike many comets that disintegrate upon approaching the Sun, 3I Atlas has exhibited consistent activity with a well-defined coma and a detectable tail. Observations from the Hubble Space Telescope and the James Webb Space Telescope, JWST, have provided detailed insights into its composition, revealing the presence of carbon dioxide, water ice, and various volatile compounds. These findings suggest that 3I Atlas is an active comet, continuously releasing material as it is heated by the Sun. The resilience of 3I Atlas raises important questions about the nature of interstellar comets and their ability to survive prolonged exposure to solar radiation. While many interstellar objects are expected to be fragile due to their long journey through the cold vacuum of space, 3I Atlas appears to have retained a level of structural cohesion that allows it to withstand the intense conditions of the inner solar system. This has led scientists to speculate about the composition and formation history of such objects, particularly whether they originate from star systems with different evolutionary histories than our own. Another fascinating aspect of 3I Atlas is its origin. Tracing its trajectory backward through the galaxy, astronomers have determined that it originated from the direction of the galactic center, specifically the thick disk region of the Milky Way. This is a significant finding, as it suggests that 3I Atlas may be among the oldest known interstellar objects. Studies conducted by researchers such as Matthew Hopkins and Asta Taylor indicate that 3I Atlas could be between 7.6 and 14 billion years old, far older than the solar system itself. If this is accurate, 3I Atlas may contain material that predates the birth of our own planetary system, offering a rare opportunity to study the remnants of an ancient stellar environment. The survival of 3I Atlas also has implications for our understanding of interstellar object detection. Prior to its discovery, most interstellar objects were expected to originate from the solar apex, the direction in which the Sun is moving through the galaxy. However, 3I Atlas's southern origin challenges this assumption, suggesting that interstellar objects may be more evenly distributed across the sky than previously thought. This has important consequences for future surveys, as it implies that telescopes must be designed to detect such objects regardless of their direction of approach. As 3I Atlas continues its journey through the solar system, it is expected to reach perihelion on 29 October 2025, at a distance of 1.36 AU from the Sun. While it will not be visible to the naked eye, it will be observed by a range of ground-based and space-based instruments, providing further data on its structure and composition. After perihelion, the comet will begin its slow departure from the solar system, eventually returning to interstellar space and continuing its journey through the galaxy. While C2025 R2 SWAN and 3I Atlas represent two extremes in cometary behavior, one disintegrating upon its first close approach to the Sun, the other surviving and continuing its interstellar journey. They both contribute to our understanding of the dynamic and unpredictable nature of the solar system. Their contrasting fates underscore the variety of factors that influence cometary survival, from internal structural strength to external environmental conditions. The study of these comets also highlights the importance of continued astronomical observation. Without the vigilance of amateur astronomers and the advanced capabilities of modern telescopes, many of these discoveries would remain hidden. Moreover, the data gathered from these objects provides valuable insights into the processes that shape cometary evolution and the broader dynamics of the solar system. As we continue to explore the cosmos, the stories of C2025 R2 SWAN and 3I Atlas remind us that the universe is a place of constant change, where the line between destruction and endurance is often razor thin. In the next section, we will delve deeper into the broader implications of these cometary events, examining what they reveal about the volatile playground of the solar system and the mysteries that still lie beyond our current understanding. The contrasting fates of C2025 R2 SWAN and 3I Atlas offer a wealth of insight into the volatile and unpredictable nature of the solar system. These two comets, while distinct in their origins and survival rates, serve as case studies in the forces that shape cometary evolution, from the delicate balance of internal structural integrity to the overwhelming influence of solar radiation and gravitational interactions. Their stories also raise profound questions about the broader mechanisms governing the solar system and the universe at large. From the origins of interstellar objects to the long-term fate of cometary bodies, one of the most immediate implications of these cometary events is the confirmation that not all comets are created equal. While some, like 3I Atlas, demonstrate remarkable resilience in the face of extreme conditions, others, such as C2025R2, succumb to the very forces that drive their activity. This variability points to the importance of internal composition and structural cohesion in determining a comet's longevity. C2025R2's disintegration near perihelion suggests that it was composed of loosely bound material, perhaps with a nucleus of low density or high porosity. Such a structure would make it particularly susceptible to the thermal stresses and tidal forces encountered as it neared the Sun. In contrast, 3I Atlas's survival indicates a more robust internal framework, possibly supported by a denser or more cohesive nucleus capable of withstanding the intense heating and mechanical stresses associated with its close approach. Beyond their individual fates, these comets provide valuable data on the mechanisms that govern cometary activity and evolution. C2025R2's brief but dramatic outburst in early April 2025 offers a rare glimpse into the chaotic nature of cometary behavior. The sudden brightening of the comet was followed by a rapid decline, ultimately culminating in its complete disintegration. This sequence of events aligns with the theory that comets can experience sudden bursts of activity due to internal fractures or the release of volatile materials trapped beneath the surface. As the comet approached the Sun, the increasing solar radiation would have accelerated the sublimation of its ices, leading to a rapid buildup of internal pressure. If the structural integrity of the nucleus was insufficient to withstand this pressure, it would have fractured, releasing a plume of gas and dust before ultimately breaking apart. This phenomenon is not unique to C2025R2. Similar disintegration events have been observed in other comets, such as Comet 73P Schwarzmann-Wachmann 3, which famously fragmented into multiple pieces in 1995. However, the precise timing and scale of C2025R2's breakup highlight the difficulty of predicting cometary behavior with certainty. Even with extensive observational data, comets can exhibit unexpected behavior, making them some of the most unpredictable objects in the solar system. This unpredictability underscores the need for continued monitoring and study of cometary objects, as even minor changes in trajectory or composition can lead to vastly different outcomes. In contrast, 3I Atlas's survival offers a different perspective on the challenges faced by comets in the inner solar system. As an interstellar object, 3I Atlas was not bound by the gravitational forces of the Sun in the same way as native comets. Its hyperbolic trajectory meant that it would not be permanently captured by the solar system, allowing it to escape after its brief encounter with the Sun. However, this also meant that it was subject to a unique set of environmental conditions. Unlike comets that originate from the Kuiper belt or Oort cloud and gradually adjust to the solar system's gravitational field, 3I Atlas entered the inner solar system at an extreme velocity, making its interaction with the Sun particularly intense. Despite these challenges, 3I Atlas has maintained a stable structure, suggesting that its composition may differ significantly from that of native comets. The presence of carbon dioxide and other volatile compounds detected by the James Webb Space Telescope indicates that 3I Atlas is an active comet, continuously releasing material as it is heated by the Sun. This sustained activity implies that the comet possesses a reservoir of volatile substances deep within its nucleus, allowing it to resist complete disintegration. The fact that 3I Atlas has survived its close approach to the Sun also raises intriguing questions about the nature of interstellar comets and their ability to endure prolonged exposure to solar radiation. Perhaps the most profound implication of 3I Atlas's journey is the insight it provides into the origins of interstellar objects. Tracing its trajectory back through the galaxy, astronomers have determined that 3I Atlas originated from the thick disk region of the Milky Way, a region dominated by older stars with lower metallicity compared to the thin disk where our solar system resides. This suggests that 3I Atlas may be significantly older than the solar system itself, possibly dating back 7.6 to 14 billion years. If this is indeed the case, 3I Atlas represents a rare opportunity to study material that predates the formation of our planetary system. The discovery of such an ancient interstellar object has important implications for our understanding of the early universe. If 3I Atlas is truly as old as some models suggest, it may contain preserved information about the conditions of the galactic disk billions of years ago. This includes insights into the chemical composition of protostellar disks, the distribution of volatile materials in early planetary systems, and the frequency of planetary ejection events. By studying 3I Atlas, astronomers may gain a better understanding of how planetary systems form and evolve over cosmic timescales. Furthermore, 3I Atlas's southern origin challenges existing assumptions about the distribution of interstellar objects in the sky. Prior to its discovery, most interstellar objects were expected to originate from the solar apex, the direction in which the Sun is moving through the galaxy. However, 3I Atlas's trajectory suggests that interstellar objects may be more evenly distributed across the sky than previously thought. This has important consequences for future surveys, as it implies that telescopes must be designed to detect such objects regardless of their direction of approach. The fact that 3I Atlas was discovered despite its southern origin also highlights the growing capabilities of modern astronomical instruments, which are now able to detect and track interstellar objects with unprecedented precision. The study of C2025 R2 and 3I Atlas also contributes to our understanding of the broader dynamics of the solar system. Both comets illustrate the powerful influence of the Sun in shaping the fates of cometary bodies. The intense solar radiation and gravitational forces that act upon comets as they approach the Sun play a crucial role in determining whether they survive or disintegrate. Additionally, these comets serve as reminders of the solar system's role as a dynamic and ever-changing environment, where objects are constantly in motion and subject to a wide range of external influences. However, despite the wealth of knowledge gained from these cometary encounters, many mysteries remain unsolved. For instance, while C2025 R2's disintegration is well documented, the exact mechanisms that led to its breakup are still not fully understood. Was it primarily the result of thermal stress, or did tidal forces from the Sun play a dominant role? Similarly, while 3I Atlas has proven to be resilient, the long-term stability of its structure remains uncertain. Will it continue to maintain its integrity as it departs the solar system? Or will it eventually break apart due to prolonged exposure to solar radiation? These are just a few of the many unanswered questions that continue to drive scientific inquiry. Moreover, the discovery of 3I Atlas raises the possibility of encountering more interstellar objects in the future. As observational technology improves, astronomers are increasingly likely to detect additional interstellar visitors, each with its own unique trajectory and composition. These discoveries have the potential to revolutionize our understanding of the galaxy and the processes that govern the distribution of planetary material across interstellar space. They may also provide insights into the frequency of planetary ejections from other star systems and the likelihood that such objects carry traces of their original planetary environments. Ultimately, the stories of C2025, R2 SWAN, and 3I Atlas serve as a reminder of the vast and largely unexplored nature of the cosmos. While we have made great strides in understanding the mechanics of cometary behavior and the origins of interstellar objects, these discoveries also highlight the limitations of our current knowledge. There is still much to learn about the forces that shape the solar system, the nature of interstellar material, and the long-term fate of cometary bodies. As we continue to study these celestial wanderers, we may uncover new insights that challenge our existing models and expand our understanding of the universe. As we draw this journey through the solar system's volatile playground to a close, the stories of C2025 R2 SWAN and 3I Atlas leave us with more than just scientific insights. They invite us to ponder our place within the vast and ever-changing cosmos. These two comets, one disintegrating in the Sun's embrace and the other forging a path through interstellar space, embody the duality of existence in the universe, the fragility of life and the resilience of nature, the fleeting and the eternal. In their brief appearances, they remind us that the universe is not a static realm, but a dynamic tapestry of motion, transformation, and cosmic cycles. The disintegration of C-2025 R2 SWAN serves as a poignant reminder of the impermanence that defines much of the universe. Just as this comet met its demise in a final burst of brilliance, so too do many celestial phenomena. Stars, galaxies, even entire worlds, follow paths of creation and destruction. Yet, even in its dissolution, C-2025 R2 contributed to our understanding of the forces that govern cometary behavior. Its brief but dramatic outburst and eventual fragmentation were not signs of failure, but rather part of a natural process that shapes the solar system. In a way, the comet's fate mirrors that of many things in life. Its journey may have ended in the sun's fire, but its legacy lives on in the data it left behind and the knowledge it imparted. In contrast, 3I Atlas represents endurance, a testament to the resilience of objects that traverse the cosmos. Its survival against the immense forces of the sun and its continued journey outward into interstellar space speak to the enduring nature of the universe's inhabitants. Though it will one day vanish from our sight, its path through the solar system will be studied for years to come, offering clues about the origins of interstellar objects and the ancient history of the galaxy. 3I Atlas's journey reminds us that even in a universe governed by entropy and decay, there is a capacity for persistence, a force that allows objects to defy the odds and continue their voyage through the void. These comets also highlight the importance of curiosity and the pursuit of knowledge. The fact that both C-2025 R2 and 3I Atlas were discovered by astronomers, both professional and amateur, demonstrates the power of observation. Every time we turn our eyes toward the sky, we open ourselves to the possibility of uncovering something new, something that reshapes our understanding of the universe, whether it is the fleeting brilliance of a dying comet or the steady progress of an interstellar traveler. Each discovery adds another piece to the puzzle of cosmic existence. Moreover, the study of these comets reinforces the idea that the universe is not separate from us. It is intricately connected to our own experiences and perceptions. The same forces that govern the fates of comets also shape the world we inhabit. The Sun, which brought about the disintegration of C-2025 R2, is the very source of life on Earth. The gravitational forces that influence the trajectories of these comets are the same ones that keep our planet in orbit and sustain the delicate balance of our solar system. In this way, the universe is not a distant and indifferent expanse, but a living, breathing entity in which we are deeply embedded. As we reflect on the cosmic clockwork of the universe, we are reminded of the humility that comes with exploring the unknown. The more we learn, the more we realize how much remains undiscovered. The fates of C-2025 R2 and 3I Atlas are but two threads in the vast fabric of the cosmos, and there are countless other stories waiting to be uncovered. Perhaps in the distant future, another generation of astronomers will look to the sky and witness a comet that challenges our understanding of the universe once more. In the end, the study of comets like C-2025 R2 and 3I Atlas is not just about understanding the mechanics of celestial bodies. It is about understanding ourselves. It is about recognizing that we too are part of the cosmic cycle, born from the remnants of stars, shaped by the forces of nature, and destined to leave our own mark upon the universe. As we continue to explore the cosmos, we carry forward the spirit of curiosity and wonder that has driven humanity since the dawn of time. And in doing so, we reaffirm our place in the grand design of the universe, not as passive observers, but as active participants in the unfolding story of existence.